Hello, everyone. You'll see this as number 5 on the atomic mass packet, and I'm going to do number 5 with you. That should hopefully help you with the rest. There is a simulation that second block did in class on Thursday that you can definitely click on in the calendar and kind of mess around with it. It's essentially what they did, and we just kind of talked about some of the things about it, but it really kind of helps with the idea of the different isotopes that exist for different elements, and then how that leads to the mass that we see on a periodic table, which is exactly what I'm going to work through with you right now. For this problem, there's some sig fig ramifications here too. So for this problem, it talks about neon and the different isotopes that neon has naturally. Um, there's 3 of them. There's one that has a mass that you see here. There's one that has a mass that you see here and a mass you see here. So I'm just going to label those real quick, and then we're going to do some calculations. So neon. This would be called neon 20, first one, neon 21, and neon 22. Those are the mass numbers of those, even though it's not labeled in the problem. You'll see that in some of your other problems. What we're going to do here is we're going to take those masses, so these are the masses of the isotopes that exist naturally, and then the percentage that they do exist naturally, and this is where the atomic mass from the periodic table comes from. So if I take the mass here, 19.992 AMU, and I'm going to multiply that by its percentage, but I'm going to move it back into decimal form to do that. And I'm going to write those numbers out in a little bit. And then I'm going to take the next one, 20.994 AMU times its percentage. Looks like it's 0.27%, so that one looks kind of weird, but we're going to go move the decimal over 2 spots, so it's 0.0027 when it's in decimal form. And then the last one's 21.991 AMU, and we'll multiply that by its percentage, which is 0.0922 in decimal form. Now I need to plug in some numbers. I'm going to do a quick little math here real quick. First one I get 18.09. I'm going to carry through all my numbers. 47592. These would also be AMUs. What we're doing here is we are figuring out how much each isotope contributes to the final mass that we see on the periodic table. And what we're going to do is add all those up in the end. This is exactly how your grades are calculated in this class and most of your classes, is by looking at the percentages you get on your tests and your quizzes or whatever else and adding them all together. I'm going to line up the decimals here, but write out all the numbers that I get on my calculator. 566.838 AMU. So I'm always going to carry through all of the numbers. With the next one, it looks like it's 21.991 times 0.0922, and that gives me 2.0275702 AMU. If I would have known that we weren't going to have school today, I would have brought home this key and I would have had all these numbers already, but I don't, because I didn't. So now I'm going to plug all those in. What I'm going to do is add all those numbers together, and that will give me my weighted average. It's called a weighted average because I'm taking the percentages of them into account rather than just taking an average of everything or of those 3 masses. So here's the weighted average that I get when I add all up those numbers up that I've already multiplied by the percentages. 20.17900132 AMU. So I added them together here. Now we need to talk about sig figs a little bit and look at what's happening. So there's 5 sig figs here, 4 in the percentage, so I'm going to put a line under the 4th sig fig just to help me remind myself how many sig figs I have in each number. Here I have 5, here I have 2. Put a line under the 2nd sig fig. The 0 is not significant. Here I have 5, here I have 3. So I'm going to put a line under the third sig fig in that number. Now I'm adding those three numbers together. So now I have to look after the decimal. 2 past the decimal, 3 past the decimal, 2 past the decimal. That leads me to have a number 2 past the decimal. And I'm going to round that to 20.18 AMU. So are there any of these isotopes that actually have a mass of 20.18? There isn't. The closest one is the one that's the most abundant, which is always going to be the case. So when we do our problems in class, we have assumed, okay, the normal or the most typical neon atom has 20 protons and neutrons together in a nucleus. That's because the weighted average gives us 20.18. In reality, none of the isotopes have that mass. It's just that the one that there's the majority of here is closest to that mass. But this is called the weighted average, and this should match up with the number you see on your periodic table for neon. So we could use this to identify an element if we wanted to. If we didn't know it was neon and they just told us these were the masses, we could identify it as neon because we could just find it on a periodic table. But these are the types of calculations you'll do on this worksheet, in addition to some more practices with isotopes and ions and protons and neutrons and electrons. But that was the new information that you'll be doing on there.